All right, number 3. I'm looking at the diagram. We have an electron heading towards a hole and a magnetic field out of the page. And it looks like we have this going to 2 different plates. So I'm thinking capacitor right from the jump. And then I'm looking at down here, there's a lot going on, so I'm probably not going to read through all the questions. So I am going to contradict myself, but that's kind of like playing it by ear. I see the battery is switched, so plate 1 becomes positive, plate 2 becomes negative, and then a proton is used instead of an electron. And then I'm going to kind of go back and read the question so I know what's going on, because right now I'm starting to get lost. If you start to get lost, go back to the question.
Okay.
In an experiment conducted, 2 tests are run. In both trials, you can ignore gravity. That's fantastic. The following is a diagram of the test. In test 1, there are 2 large parallel plates separated by this distance, 0.5 meters. That's not drawn on the diagram, so I'm going to put that up there. With a potential difference of 0.12 volts across them. There is a uniform magnetic field pointing perpendicularly out of the page with a strength of 0.002 teslas. So 0.002 teslas is the magnetic field strength. I'm going to draw that on. Starting to the right of the plate. So as soon as it gets through this little hole, and this one's going to be positive because that's how capacitors work. The positive charges the positive side, the negative side becomes negative, right? So now we have the voltage of this capacitor. There's an electron is released from rest at plate 1 as shown above. It passes through a hole in plate 2 and enters the magnetic field, and it only experiences forces due to the magnetic field. That's great. Once it's through the hole, we only have one force acting on it.
Okay.
So now there's a second test, the same setup, except now the battery is switched. So the plate 1 becomes positive. So I'm going to change color just so that stands out. So orange will be test 2. So this becomes positive, and this becomes negative. And we're going to use a proton, which makes sense. Proton will also be ejected from the positive side or pushed away from the positive side.
Mm-hmm.
So either way, they're both being pushed to the right. And now I'm jumping into A. As the particles move from plate 1 toward plate 2 in each test, they experience unbalanced forces. Unbalanced forces cause acceleration because net force is equal to mass times acceleration. Hopefully that equation is drilled into at this point. Causing their speed to change. Well, that's the acceleration. After plate 2, they still experience unbalanced forces, but their speed doesn't change. Use the concept of work to explain how this occurs. So what's your thought?
So they no longer they don't change speed. So speed is the scalar quantity, but there's work being done. So I'm assuming it's still accelerating, which tells me it's probably changing direction.
Bingo. That's exactly it. Now, again, underlining key things. Use work to explain why this happens. So why does it change speed when it's in the gap, but it changes direction when it's in the field using work?
Let's see. The magnetic field is applying a force, so whenever there's a force applied, there is also work being applied? That feels like a stretch.
Unbalanced forces will do work on a particle. So the electric field force is what's happening inside the gap, and the magnetic field force is what's doing the work over here.
Okay, so the force electric field is what's initially accelerating it until it's past the gap, and then once it's out of the gap, it's the magnetic force that's causing it to accelerate.
Correct.
But it's okay.
But they need you to use work to justify why it's linear in the gap, but changing direction in the hole.
Okay.
And that.
Well, you could.
Go ahead.
All right. So basically, the electron is just a straight line repulsion, just straight away from the positive repelling away from the positive. Just use the proton, for example. And then once it's outside of the electric field, which is, we're going to assume this is a capacitor, just for argument's sake. Once it's outside the capacitor, it's in the effects of the magnetic field rather than the electric field. And the magnetic field, using the right-hand rule, is going to want to apply a different type of work, which this is going to make it change angle because we're given that speed stays constant.
Yes, but again, you have to very clearly. I mean, they're asking why the work of the electric force is linear and the work of the magnetic field is not linear. And right there, I'm looking at the equation for work, which on your equation sheet is work is equal to FD cosine theta. That's your key right there. So in the first, and where the angle theta is the angle between the force and the distance that the particle is traveling. So while you're in the gap, the force, the electric force, is to the right, and the distance is to the right. So they're parallel to each other. Whereas in the other situation, the force and distance are perpendicular to each other. So it doesn't change the speed, it just changes the direction.
Oh yeah, magnetic field is perpendicular. Okay.
Yeah, and you even said that. You said using the right-hand rule. You were talking about that, but you didn't specifically state that the force is perpendicular to the velocity.
Okay.
Or the direction of movement. Huh?
That's going to be a fun to remember, like, on the spot, but I'm going to start drilling that into myself tomorrow.
It's so much to remember. It's an entire year's worth of information. But
yeah, I'm usually good.
Go ahead, I'm sorry.
I'm usually good at, I sit down to the test, I can buzz through the multiple choice. Even if I try and slow myself.
I would go ahead and go for it. Yeah. Use what works for you. Use your strengths.
Okay.
All right, so B, which I think is the most involved question on this entire practice exam, is you need to find the ratio of the speed of the proton from the hole to the speed of the electron as it emerges from the hole. This is a key word you always need to look at. If you see ratio, circle it, because it means one thing. Huh?
You need to solve for both and then take like a percent.
Yep.
You need to solve for both.
It's just one divided by the other. So the velocity of the proton divided by the velocity of the electron. That's what you're trying to do. So since they say find it, that means we have to actually calculate it. So, yeah, this one is very involved. Huh?
I'm looking at something here because both are going to be exiting at the same velocity, correct?
It would seem that way.
Sorry, let me rephrase that. They both have the same charge.
Correct.
So you calculate the electric magnetic force. The only difference between the two is the mass. So could you do the ratio of their masses?
That's the exact right idea. That's it. Yes, their mass affects it because the net force is mass times acceleration. So if one has more mass, it's going to have less acceleration as a result. So right off the jump, you should know that this ratio should be less than 1 because the velocity of the proton has to be less than the velocity of the electron. All right, so you can go right from this equation, or you could go from the work equation. both will basically get you, not will basically, both of them will get you to the same result.
Okay.
So, oh my goodness, this should be QE. I'm sorry, I wrote Q over E. I don't know where I was going with that. But force is QE, right? Or is it QV? The force from an electric field. QE. But we don't have that, do we? Do we have the strength of the electric field?
It's irrelevant because it's being applied to both of them, so we can assume it to be any value we want for our calculations, couldn't we?
The force is constant, you're right. Okay. So that means that mass is inversely, or acceleration is inversely proportional to mass from this equation. So then we need to plug in, well, acceleration is the final velocity minus the initial velocity. So then, but that doesn't take into account the v squared.
Yeah, no, we can assume an arbitrary value of E because the electric field, whatever it may be, is being applied to both molecules.
That's constant, and the charge is equal. So they have the same force, so acceleration should be inversely proportional to mass. But we don't have time. So we don't have time and we don't have final velocity. But wait, if they have the same force, they have different mass. Huh?
So we can, here's how I'm thinking. If we solve for the force of electricity, the electric force, so we can assume an arbitrary field. So we'll put a number in for E. We'll call it 2 for this example. And then you multiply it by the charge. They're both going to have the same force. And then we can use force equals mv squared.
Right.
To solve for the velocity, since we know that both of the mass of a proton and the mass of an electron are both known.
You can't use it, though. Because even if you calculate an arbitrary force, you can't use that to determine the acceleration because they would have different final velocities and different times, which means you still have 2 unknowns. So you can't do it that way. So in that case, we have to use work energy.